This diagram shows the architectural boundary of our system. On the left is the MindShard agent, the operator runtime acting as the hands and eyes. On the right is the BDNeuralSUITE, a specialized long-term memory organ. This is a departure from a standard setup. An advanced agent does not simply call a database. It operates within a controlled runtime that delegates its memory formation entirely to the substrate. The suite's pipeline operates in 3 distinct phases: the ingestion of evidence, the formation of mathematical edges, and physiological retrieval. Context windows eventually fill up and discard older information. To sustain reasoning over time, an agent must delegate its long-term state to a dedicated physiological structure. Standard Retrieval Augmented Generation, or RAG, takes documents and slices them into flat text chunks. This process destroys the structural, grammatical, and causal context of the original source code or prose. Standard retrieval relies on top K cosine similarity. This is a mathematical method that measures the distance between a query and a data point in vector space. It returns the closest data, but it cannot explain why that specific data is related to the prompt. Building an inspectable memory substrate requires redesigning how data is parsed from the source, how relationships are scored between those pieces of data, and how evidence is ultimately retrieved. Treating memory as disposable text strings imposes a hard ceiling on an AI agent's ability to navigate complex codebases or sustain long-term interactions. This diagram shows a flat block of source code transforming into a hyperhunk. A hyperhunk is a hash-stable content address node. It serves as the atomic unit of the system, storing data across 5 distinct layers. Traditional parsers operate in a waterfall format, selecting one format and discarding the rest. The splitter utilizes a parallel surface population model, running 3 engines: tree-sitter, peg, and fallback simultaneously. The tree-sitter engine populates the grammatical surface. It extracts abstract syntax tree, or AST, data. This captures the exact scope stacks, docstrings, and base classes directly from the source code. Simultaneously, the PEG engine populates the structural surface. It tracks the exact hierarchical path of document headings and explicit cross-references within the text. The fallback engine always runs alongside them to lock in the verbatim text string as a guaranteed baseline. These engines operate under a strict rule of non-competition. They do not overwrite each other. They overlay simultaneous truths onto the exact same node. By capturing the verbatim text, the grammar, and the file structure all at once, the data retains its original meaning. The context survives regardless of the retrieval mechanism the agent uses later. Once the surfaces are urged, the node hits the negotiator. The negotiator is the sole token budget authority, executing only after all parsing is complete. This diagram shows the sliding window overlap mechanism. BPE, or byte pair encoding, tokens are subword units used to read text. By copying tail tokens of one block into the header of the next, the negotiator prevents hard context-breaking cuts. If a hunk exceeds the token budget, the negotiator splits it into smaller fragments. It explicitly retains their lineage via structural parentage metadata, connecting every child fragment directly back to the original parent node's ID. In a graph memory system, truncation must be treated as a deliberate first-class memory event. This prevents the creation of orphaned contextless data fragments. This diagram illustrates the graph assembler writing hyperhunks into the SQLite cold artifact. The database schema separates the data into distinct content nodes and localized occurrence nodes. To prevent O(n)² scaling issues, the assembler uses a sly-in window comparison. A new node evaluates itself strictly against a buffer of the 50 most recent prior nodes. The component responsible for scoring these pairs is the bootstrap nucleus. It serves as the deterministic interaction axis for the entire graph. This diagram shows the primary outputs of the nucleus. When a pair clears the threshold, it forms an edge with a numerical connection strength and a categorical interaction type label, such as grammatical dominant. The edge also stores a routing profile. This is a JSON payload, a lightweight text format for structuring data that mathematically records the exact fractional breakdown of which surfaces caused the connection. A graph is only as useful as its inspectability. Storing the precise reason for an edge allows an agent to look at a piece of resurfaced memory and understand exactly why it was retrieved. Currently, the Phase 1 bootstrap nucleus uses fixed, builder-tunable weights to evaluate connections. It does not use a learned neural network. This is a deliberate architectural restraint. The implementation of a learned feed-forward network, or FFN, is intentionally deferred to Phase 2. This diagram shows what happens as real code corpora run through the deterministic nucleus. It generates and archives traceable, pairwise interaction evaluations, building a massive training dataset. Deferring the neural network ensures that future learned weights will be grounded in verifiable, explainable relationship logic rather than black box assumptions. When retrieving evidence, the system uses the hot engine. It abandons plain nearest neighbor search entirely, opting to load localized subgraphs directly from the cold artifact. This equation is the core GraphBLAS update formula. GraphBLAS is a standard API that expresses graph operations as linear algebra. This equation governs how activation propagates through the memory nodes. In this formula, H is the live activation vector across the nodes. The alpha variable is the decay multiplier, representing the system friction or dissipation over time. A is the adjacency matrix. This contains the excitatory signals, the structural pathways and nucleus-scored edges pulling energy forward to activate related nodes. H is the inhibition matrix. It represents contradiction pressure derived from NPMI co-occurrence data. NPMI stands for Normalized Pointwise Mutual Information, a statistical measure of how often two terms appear together versus apart. This matrix suppresses irrelevant nodes. To prevent runaway feedback, the engine applies cyclic prevention safeguards and hard hop limits. These terminate the propagation loop exactly when the activation stabilizes. The final output is the bag of evidence. This is a ranked list of occurrences shaped entirely by structural gravity and semantic resonance. Physiological retrieval surfaces context based on active relational logic rather than static proximity. It mimics true associative memory. This visual represents the beginning of the pipeline, raw source code entering the splitter to be transformed into multi-surface hyperhunks. Those hyperhunks pass through the bootstrap nucleus, forming mathematically explainable edges within the SQLite cold artifact. When a query occurs, the hot engine pulses with matrix activation, using excitatory and inhibitory pressure to extract a finalized bag of evidence. That bag of evidence passes back across the architectural boundary, injecting directly into the Mindshard agent runtime for execution. Preserving the verbatim, grammatical, and structural context simultaneously avoids the inherently lossy nature of flat text chunking. For an AI agent to perform complex reasoning over time, its memory cannot be a static database. It must be engineered as a durable, inspectable, living organ.